Welcome, everyone. I'm excited to introduce today's presentation. We'll be discussing our MCG, which is revolutionizing cardiac testing. It's your 21st century replacement for the traditional 130-year-old EKG and most of your cardiologists' legacy stress imaging tests. Over the next few slides, we'll explore how this technology is transforming heart health diagnostics, offering faster, more accurate, and more comfortable solutions. Let's dive in. Imagine waking up suddenly in the middle of a nightmare, and it hits you. What once seemed like a functioning system has now become something entirely different. It's like it's been captured, not by good intentions, but by corruption and decay. I like to think of it as an institutionally captured stinky rotten egg, something that's supposed to be beneficial, but has become toxic and rotten from the inside out. This realization is pretty stark, and it underscores a crucial point. We are facing an urgent and desperate need for change. This isn't just about minor tweaks or superficial fixes. It calls for a systemic and fundamental transformation. We need to rethink, reimagine, and rebuild the very foundations of our institutions, because the current state is no longer sustainable. This slide really ties into the overall theme of the presentation, calling for deep, meaningful change to create a better, healthier future. I beg for your willing suspension of disbelief. What I'm about to show you might seem like it's straight out of a horror movie, but I promise you, it's not. What you are witnessing is not a horror movie after all. This is real, and it's happening in the context of what we're exploring today. I want you to keep an open mind and accept this as part of the bigger picture. Often, when we delve into complex or shocking topics, our first instinct might be to dismiss or be frightened. But I ask you to suspend that instinct temporarily, so we can truly understand the significance of what's being presented. Remember, this slide is about challenging your perceptions and encouraging you to see beyond the surface. It's a reminder that sometimes truth can be stranger or more unsettling than fiction, but that doesn't mean it's not real or important. So let's proceed with curiosity and an open mind. Einthoven's 130-year-old hypothesis has not been proven. So the question remains, is the LA lead truly capturing the electrical activity from the left atrium? Or could it just be picking up signals from a bunch of neutral amino acids? Honestly, no one knows for sure. And more surprisingly, no one has definitively proven that the isoelectric point even exists in this context. This is a big deal because the entire field of electrocardiology depends heavily on this unproven hypothesis. Now, when we ask where exactly this activity is located anatomically, it becomes even more complex. Because if we don't have concrete proof about what we're measuring or where it comes from, our understanding of the heart's electrical signals is fundamentally uncertain. This highlights how much we still need to explore and verify in this field, especially since so much of our clinical practice relies on these assumptions. Applying system theory represents a genuine paradigm shift in how we understand and analyze the heart. It's about using a guiding science to discover and quantify those hidden dimensions and features of the system that traditional methods might overlook, and doing so mathematically. MCG, or multifunction cardiogram, is at the forefront of this shift. Unlike the traditional EKG, MCG applies a systems theory approach, which means we're looking at the heart not just as an isolated organ, but as part of a complex system interacting with numerous internal and external factors. This approach uses advanced mathematical models based on Euler, Lagrange coordinates. These coordinates help us analyze the system's behavior more precisely. We then combine these results through 6 mathematical transformations, which involve merging the coordinates via a Laplace transform. This process allows us to capture the system's dynamic behavior comprehensively. The key idea here is viewing the heart's interaction with its environment as a whole system, rather than separate parts. MCG measures the energy and power-generating network of this complex organ system by applying multiple mathematical functions, each representing different functional domains or aspects of heart activity. These functions reveal details that other methods might miss. Finally, we incorporate principles from Norbert Wiener's control theory, which is fundamental in computational systems and electrophysiology engineering. By combining these two equations with Wiener's control principles, we're able to model and understand the heart's behavior more holistically, capturing its intricate interactions and responses. In essence, this approach is about shifting from a linear, isolated view of the heart to a systems-based perspective, which opens up new possibilities for diagnosis, understanding, and treatment. Let's take a closer look at MCG's 6 mathematical transformations. Each of these functions provides us with uniquely specific and detailed insights into the heart's physiology as a biological organ system. They help us detect, measure, and monitor supply and demand imbalances, regardless of the cause. First, we have the phase angle shift, which helps us understand the timing relationship between signals. Next is the impulse response, showing us how the system reacts to a brief stimulus. The cross-correlation measures the similarity between two signals over time, which is crucial for identifying relationships. The coherence function tells us how well two signals are related in the frequency domain, indicating the strength of their connection. The transfer function describes how input signals are transformed into outputs, giving us a dynamic view of the system response. Now, you'll notice some mathematical expressions. P equals the inverse Fourier transform of Txy, and Vxy is the inverse of Gxy. These relate to how signals are processed mathematically. The gamma squared represents the ratio of Gxy squared over the product of Gxx and Gi, which helps quantify the correlation strength. Txy, the transfer function, is derived by dividing Gxy by Gxx, and the phase angle θ is calculated using the arctangent of the ratio of the imaginary to the real parts of Txy. Lastly, Gxx is the auto power spectrum, which involves the spectral density of a signal, essential for understanding the power distribution across frequencies. Overall, these transformations equip us with powerful tools to analyze and interpret the complex physiological signals of the heart, enhancing our ability to monitor and diagnose cardiac function effectively. What is Premier Heart's multifunction cardiogram, or MCG, technology? Well, it's the result of many years of dedicated research and development, supported by extensive data collection, thorough vetting, and supervised machine learning. This rigorous process helps us develop highly reliable algorithms that can assist clinicians in diagnosing, monitoring, and quantifying dysfunctions in both the heart and brain systems. These algorithms work physiologically, meaning they analyze real-world clinical data to give us accurate insights. MCG is a powerful tool. It's fully empirical, meaning it's based entirely on objective data rather than guesswork. It's designed to be reliable and highly accurate, serving as a bedside diagnostic superdomain that uses artificial intelligence to provide comprehensive insights. What makes it so remarkable is its ability to identify all stages of heart disease, right from the earliest signs of systemic imbalances, those subtle supply and demand mismatches that can signal the beginning of trouble. The ultimate goal of this technology is to detect diseases early, so early that we can prevent their progression, and ideally, reverse them before they become severe. By doing so, we aim to eliminate premature deaths and improve long-term health outcomes. This aligns perfectly with our overall mission, using innovative technology to transform how we diagnose, treat, and prevent cardiovascular diseases. Let's talk about systems computational physiology. We've developed a computational model that replicates the complex biological mitochondrial network. Now, this network in the human body is astonishing. It's made up of between 70,000 and 100,000 trillion mitochondria, or about 100 quadrillion individual units. These tiny powerhouses are constantly working to generate energy for our cells, tissues, and organs, ensuring that we survive and function 24/7, every day of the year. Premier Heart's MCG is built around 6 core functions across 6 different domains. These form the foundation of the 12 phases we use. Think of these phases as branches of a sophisticated computational system. This system allows us to observe, measure, quantify, and monitor the energy production dynamics of the entire mitochondrial network, 24/7, if necessary. Over decades, we've gathered a wealth of data. Using that, we've crafted highly refined, physiologically sound algorithms. These algorithms are objective, optimized through a rigorous, ethical, data-driven mathematical framework that adheres to real-world principles. And at the heart of everything, we follow a simple but crucial rule. First, do no harm. This ensures that our approach is not only scientifically robust, but also ethically responsible. This system, this model, helps us understand these vital energy processes, ultimately supporting better health outcomes. Let's delve into the core of our system design. It's entirely built on a set of fundamental mathematical principles combined with empirical data, ensuring both robustness and accuracy. The Premier Heart's MCG platform is designed as a do-no-harm, bedside diagnostic tool, meaning it prioritizes patient safety while providing intelligent support for diagnosis. This system leverages advanced techniques like decryption and fast Fourier transform, or FFT, to analyze the data efficiently. The final diagnosis is presented as a severity score, which ranges from 0 to 22, giving clinicians a clear, quantifiable measure of the patient's condition. An automated diagnostic report is generated in PDF format, streamlining the process and making it easy to review and share. For data acquisition, leads II and V5 are recorded for about 82 seconds, capturing essential cardiac signals. All of this happens in roughly 10 minutes from start to finish, making it a quick yet comprehensive assessment. The data is transmitted, analyzed, and received almost instantaneously, thanks to the rapid digital process. The file is amplified, digitized, encrypted, and transmitted securely via the cloud, ensuring data integrity and safety. Our cloud database has now been updated to include over 250,000 cases, continuously improving the system's accuracy. Most impressively, our team has empirically discovered around 10 quadrillion parameters, a staggering number, representing 10 times the energy capacity of the entire mitochondrial network in animals and humans. And the system operates around the clock, 24/7, throughout the year, providing continuous, reliable support for critical cardiac diagnostics. Now, let me take a moment to explain some of the fascinating discoveries our MCG technology platform development team has made. Through extensive exploration across 6 distinct domains and 12 phases, we've empirically identified a vast array of digital parameters. These parameters, what we've whimsically called the quinquagitillion, are at least 10 times more numerous than the biological mitochondrial network found within our cells. To put that into perspective, this level of numerical complexity is 10 to the 68th power times greater than the number of Google search results. Just imagine how vast and intricate the biological mitochondrial network must be to handle such complexity. What makes this discovery truly unprecedented is its potential to fundamentally transform healthcare in the 21st century. By understanding and harnessing these digital parameters, we're opening the door to innovations that could redefine how we diagnose, treat, and prevent disease. This is not just a leap forward. It's a paradigm shift that could revolutionize the entire landscape of healthcare. AMPK is truly a master switch for our metabolism and genetic survival throughout our entire lives. It plays a crucial role in keeping us healthy by regulating energy balance and ensuring our cells function properly. What's fascinating is how closely AMPK is associated with mitochondria, the powerhouses of our cells, helping to sustain important processes like autophagy, which is our body's way of cleaning out damaged cells and recycling components. This connection supports cellular metabolism and helps clear waste materials, both vital for longevity and overall health. What's really groundbreaking is that we're now able to detect these expressions of AMPK, even though they were previously impossible to see. This advancement allows us to better understand how this master switch operates within the mitochondrial network. This discovery is unprecedented. It fundamentally transforms how we approach healthcare, shifting towards a more personalized, precise system. Through this, we've developed a foundational system that paves the way for 21st century lifestyle medicine, enabling us all to thrive by optimizing our health at the cellular level. This is truly a leap forward in how we can maintain wellness and longevity in our modern world. Let's take a closer look at mTOR, or mammalian target of rapamycin. This is a protein kinase, which means it's an enzyme that modifies other proteins by adding a phosphate group. Its main role is to regulate key cellular processes like growth, proliferation, and metabolism. Importantly, it responds to signals from nutrients and growth factors, helping the cell adapt to its environment. mTOR doesn't work alone. It functions as part of two distinct complexes called mTORC1 and mTORC2. Each of these complexes has unique roles in the cell. mTORC1 is primarily involved in controlling protein synthesis, cell growth, and overall metabolism. Think of it as the master switch for building and expanding the cell. On the other hand, mTORC2 plays a different but equally vital role. It's involved in cell survival, organizing the cell's cytoskeleton, which is like the cell's internal scaffolding, and also in insulin signaling, which is crucial for energy regulation. These complexes are fundamental to many cellular processes, including autophagy, which is the cell's way of cleaning out damaged components. So, understanding mTOR helps us see how cells grow, survive, and maintain balance. And connecting this to our overall theme, this discovery opens up new possibilities in healthcare, potentially transforming how we treat diseases related to cell growth and metabolism. It's truly an unprecedented breakthrough that could change everything. The MCG score will change in line with changes in the patient's condition. What this means is that, as a patient's health evolves, their MCG score reflects those changes accordingly. It's a dynamic measurement that provides real-time insights. We can use this score to monitor the patient's condition closely, making it a valuable tool for tracking progress or identifying potential issues early on. Essentially, the MCG score serves as a continuous feedback loop, helping us make more informed decisions and tailor care to the patient's current needs. This ongoing monitoring aligns perfectly with the overall goal of personalized, responsive healthcare. Let's take a closer look at the different types of ischemia. On one hand, we have global ischemia, which affects the entire heart muscle, often due to severe conditions like cardiac arrest or systemic low blood flow. On the other hand, local ischemia targets specific regions, usually caused by blockages in coronary arteries leading to localized damage. Now, shifting to disease severity, various conditions can impact the heart's function significantly. For example, atrial fibrillation disrupts normal atrial rhythm, potentially leading to blood clots and stroke risk. Atrial ventricular fibrillation involves the irregular activity between the atria and ventricles, which can be life-threatening. We also see cardiomyopathies, which are diseases of the heart muscle itself, affecting its ability to pump effectively. This slide includes some important tables that detail specific conditions like congenital heart disease, incipient arrhythmias, and potential fibrillations, early signs that can develop into more serious rhythm disorders. Other conditions that cause myocardial damage include myocarditis, which is inflammation of the heart muscle, and pulmonary or rheumatic heart diseases that can compromise heart function over time. Ventricular arrhythmias, such as ventricular fibrillation and incipient ventricular fibrillation, are particularly dangerous because they can lead to sudden cardiac death. Ventricular hypertrophy, which is the thickening of the ventricular walls, often results from chronic pressure overload, like hypertension. Acute power failure refers to sudden drops in the heart's ability to generate enough force, leading to decreased cardiac output. Arrhythmias such as bradycardia, a slow heart rate, and tachycardia, a fast heart rate, are also critical to recognize. These can cause decreased ejection fraction, meaning less blood is pumped out with each beat, and changes in myocardial compliance, which affects how the heart relaxes and fills. We also observe asynchrony, which refers to the uncoordinated contraction of different heart regions. Global asynchrony involves the entire heart, like when the delay appears in lead V5 compared to lead II, or vice versa. Local asynchrony affects specific areas, indicating regional conduction delays. Finally, myocardial remodeling is a key process where the heart structure changes in response to injury or stress, often leading to further dysfunction. All these factors are detailed in the MCG report, including the so-called 18 red indications, which highlight new discoveries in myocardial conduction. Understanding these points helps us grasp how various ischemic and structural abnormalities contribute to overall heart disease severity and guide us toward better diagnosis and treatment strategies. What is the real difference MCG makes in diagnostic medicine for the 21st century? Well, let's start by looking at traditional methods. We rely on blood tests, X-rays, MRI, CT scans, and PET scans. These techniques have served us well, but they also have significant limitations. They often leave us with information blind spots, meaning there are critical details about a patient's health that we simply can't see with these tools. This is where MCG comes in. MCG fills in those gaps and eliminates the blind spots, providing the vital missing information we need. It focuses on micro and macro molecules within bodily fluids, giving us a much deeper understanding of what's happening at a molecular and systemic level. Traditional imaging like X-ray or MRI shows us the anatomical structure, but they only offer partial functional information. They don't tell us how those structures are actually functioning. And for a long time, we've been missing the full picture of the body's functional systems and physiology, information that's been critically absent since the beginning of time. So what MCG does differently is that it bridges that gap, delivering comprehensive, vital insights that go beyond just structure. It allows us to see how systems are working, not just how they look. This is a game changer in diagnostic medicine, helping us make more accurate diagnoses and better informed treatment decisions. Let's take a closer look at how different stress testing methods compare in terms of sensitivity, specificity, and practicality. As you can see from the table, MCG, or magnetocardiography, stands out with a sensitivity ranging from 90 to 100%, meaning it's very effective at detecting true positives. Its specificity also ranges from 85 to 97%, which helps in reducing false positives. In real-world settings, MCG maintains high accuracy, around 90 to 100%, making it reliable for clinical use. When it comes to time, MCG is quite efficient, taking less than 10 minutes per sample, and it's also cost-effective, generally between $300 and $500. One of the most exciting points about MCG is its potential for early detection and prevention. Unlike other stress tests, which often only confirm existing issues, MCG can be used for early detection, allowing intervention before symptoms become severe. It's also uniquely suited for home use, which makes it accessible and convenient, especially for ongoing monitoring. Additionally, since MCG is performed at resting heart rates, it's less invasive and doesn't cause symptom exacerbation, making it safer and more comfortable for patients. This ability to monitor treatment effectiveness right at the bedside is a significant advantage, enabling clinicians to make real-time adjustments. Overall, MCG offers a combination of high accuracy, safety, convenience, and early detection capabilities, aligning well with our goal of improving cardiac care through innovative, accessible technologies. Let's take a closer look at why this comparison really matters. On this slide, we're contrasting MCG with traditional allopathic heart tests like nuclear scans, echocardiograms, stress tests, CTA, and CAG. First, when it comes to accuracy, MCG provides a range of about 85 to 100%, which is quite impressive, especially considering it's a non-invasive bedside test. In contrast, these legacy tests often have lower accuracy, with false positives reaching around 62%, and they also have high false negatives. This means they can miss critical issues or suggest problems that aren't there, creating huge blind spots in diagnosis. Next, consider the time and scalability. MCG takes roughly 10 minutes right at the bedside and can be scaled easily across many patients without the need for special facilities. On the other hand, traditional tests often require multiple visits over weeks or even months, making them much less practical and more burdensome for both providers and patients. Patient safety is another crucial point. MCG is completely safe. No stress induction, no IVs, no radiation, and no exposure to harmful drugs. Conversely, traditional tests often involve stress testing, radiation exposure, and sometimes invasive procedures, which carry risks of injury or even more serious complications like death. In terms of testing setting, MCG can be done almost anywhere, at a clinic, at home, or anywhere with internet access, making it highly accessible. Legacy tests need specialized facilities and equipment, which aren't available to everyone, limiting access and convenience. Cost is also a major factor. MCG costs typically between $350 and $450, which is just a fraction of the copay for traditional tests, which can run into tens of thousands of dollars. This makes MCG not only safer and faster, but also much more affordable. Finally, regarding primary usefulness, MCG is excellent for early detection and ongoing monitoring, helping prevent issues before they become severe. Traditional tests often detect problems too late, after significant damage has already occurred. So, in summary, MCG offers a safer, faster, more accurate, and cost-effective approach to heart health, aligning perfectly with our goal of early prevention and better patient outcomes. Overcoming barriers to entry in the medical device space has been a long and challenging journey. It's been a process that's often felt impossible and arduous, but through perseverance, we've achieved what once seemed out of reach. Our solution is infinitely scalable asterisk, thanks to cloud technology, which allows us to grow and adapt without limits. We've secured 13 patents to protect our innovations, and our hardware is market-ready, ready to make a real impact. We also benefit from existing distribution channels, which help us reach healthcare providers efficiently. Regulatory approval has been a critical hurdle, but we've obtained FDA approval and ISO certification, ensuring safety, quality, and compliance. Additionally, securing a CPT code means our device can be billed through insurance, making it more accessible to patients. One of our most valuable assets is our proprietary patient database, built over 20 years. Recreating this database would cost around $250 million and take decades, which highlights how significant our existing data advantage is. All of this has been made possible through over 2 generations of dedicated developers and decades of research. From the late 1960s to the 1990s, during the AI winter, countless teams developed multiple hardware and software iterations, refined their designs, and validated their solutions through rigorous clinical trials, phases I through IV. This history of relentless effort and innovation underscores the enormous barriers we've overcome and the foundation we've built for the future of this technology. Let's talk about the founder's vision behind this innovative approach. The lead inventor, who was once a legacy physician, made a pivotal decision in 1998 to step away from traditional conventions. His goal was to develop much more effective methods for reducing misdiagnosis, which is a major challenge in healthcare. He wanted to prevent harmful late-stage treatments that often come too late to be effective. He also aimed to eliminate diagnostic blind spots and errors, those hidden gaps that can seriously impact patient outcomes. And importantly, he focused on lowering heart care costs, making advanced care more accessible and sustainable. This vision is built on decades of solid empirical evidence, meaning it's backed by a lot of data and real-world results. Plus, it's been verified and validated through independent, reproducible tests, so it's not just claims, it's proven by both internal teams and external experts. And perhaps most compellingly, this effort is supported by satisfied paying customers who see the value firsthand. All of this reflects a deep commitment to improving heart care, driven by a clear, forward-thinking vision from Dr. Joseph T. Shen, the founder of Premier Heart. This vision aligns perfectly with our overall mission to transform and elevate the standards of cardiovascular diagnosis and treatment. In 2011, the AMA CPT panel assigned MCG a questionable CAT III code. This code described a process involving computerized database analysis of multiple cycles of digitized cardiac electrical data, collected from 2 or more ECG leads. It also included the transmission of this data to a remote center, the application of multiple nonlinear mathematical transformations, and assessments of coronary artery obstruction severity. This new description was actually approved in 2013 with the support of the Rhythm Society, which was a significant step forward. The CPT code assigned was 206T. However, what's important to highlight here is that our technology truly deserves a permanent CAT I CPT code. This would recognize its value and encourage broader adoption. Overall, this slide underscores the challenges we faced with coding and reimbursement, but also the progress made through collaboration and scientific validation. It's a key part of the bigger picture of advancing cardiac diagnostics and ensuring our innovations are properly recognized and supported. In 2012, Highmark Medicare took a significant step by independently drafting this local Medicare coverage policy. It was quite a bold move and actually sparked quite a controversy, what we might call a firestorm in the industry. The key point here is that the policy explicitly states that providers using this particular technology must agree not to send patients for certain tests. They also must refrain from performing these tests themselves within 6 months of doing a multifunction cardiogram. Now, the tests they're referring to include stress tests, whether exercise, pharmacologic, or nuclear. Also, stress echocardiograms are included, unless there's a documented structural heart defect that's the primary concern. So, if that's the case, it's an exception. Finally, the policy bans the use of multi-slice computed tomography within that 6-month window. Overall, this was a pretty significant move, as it directly impacted clinical decision-making and the use of advanced imaging and testing, raising questions about how such policies influence patient care and provider practices. This slide really highlights how a single local policy can cause a lot of debate and ripple effects across the industry. When we look at how this technology has been independently and ethically evaluated, it's quite impressive. Many high-quality investigators around the world have published research supporting its effectiveness. For example, studies in respected journals like the British Medical Journal and Circulation have shown positive results. These investigations come from various regions, including Asia, the US, and Europe, which highlights its broad international acceptance. The research demonstrates that the multifunction cardiogram, or MCG, is considered useful both for diagnosis and screening purposes. What's particularly important here is that the evaluations focus on non-invasive methods, which means patients can be assessed accurately without invasive procedures. The key takeaway is that multiple high-caliber studies have validated MCG's high accuracy in detecting relevant coronary issues. This extensive body of evidence reinforces how credible and reliable this tool is, fitting well into our overall goal of improving diagnosis with safer, non-invasive options. It's a testament to the growing global confidence in MCG as a valuable diagnostic tool. Let's explore the market insight here. The future of heart health care is heading towards a much more ethical and safer approach. It's becoming increasingly digital, scalable, and cost-effective. This new paradigm emphasizes accuracy, timeliness, and objectivity, relying on empirical, data-driven methods. Importantly, it's grounded in independent, trustworthy verification and validation to ensure reliability. What this means overall is a shift that allows lifestyle medicine to not just manage, but actually prevent and reverse diseases. This is a critical change from traditional methods. Now, looking at the legacy market, this shift is set to dismantle the outdated chain of toxic practices. Historically, we've seen a focus on symptomatic management, treating the symptoms without addressing the root causes of disease. That approach often leads to ongoing cycles of treatment without true healing. And unfortunately, the problem is compounded by ruthless late-stage sickness-seeking profiteering, which often prioritizes profits over patient outcomes, regardless of the worsening health consequences. This approach causes real harm, with millions of Americans, around 800,000, either dying or being maimed each year due to medical errors, particularly misdiagnosis. So, in essence, this new paradigm aims to eliminate these blind spots, reduce harm, and promote a more proactive, accurate, and ethical approach to heart health care. Impossible is not a fact, it's an opinion. That's a powerful reminder that many of the limitations we see are actually beliefs, not facts. As Arthur Schopenhauer famously said, all truth goes through 3 stages. First, it is underestimated, then it faces vehement opposition, and finally, it's accepted without needing further explanation. This pattern is so relevant to our journey. Throughout history, what was once considered impossible has become reality because people challenged those initial beliefs. For example, experts often say that certain innovations are impossible until around 2050. But what we've shown is that these predictions don't have to be set in stone. We've already proven them wrong by pushing beyond those perceived limits. This connects directly to our overarching theme: never underestimate what we can achieve through persistence and vision. It's a reminder that many breakthroughs start as opinions we have the power to change. And this is just the beginning. What I mean by that is, we've made significant progress so far, but there's so much more on the horizon. If you don't look to the east, you won't see the sunrise. That metaphor reminds us to stay alert to new opportunities and innovations coming our way. Many around the world are already awakening to these changes, embracing new ideas and leadership. Now, it's crucial that American cardiologists wake up and follow the leaders who are pioneering these advancements. Resistance to change might seem comfortable or familiar, but trust me, resistance is futile. We need to adapt, innovate, and lead the way ourselves. Because if we do, the future ahead is bright for everyone. This isn't just a hopeful statement, it's a call to action. Together, we can shape a future of better health outcomes, greater collaboration, and endless possibilities. So let's keep our eyes on that sunrise and move forward with confidence and purpose. Thank you all for your attention and engagement today. We truly believe in balancing creativity and innovation with the utmost priority and attention to our system's effectiveness and patient safety. Our goal is to introduce solutions that push the boundaries of what's possible, but always with the patient's well-being at the center. Our MCG is designed as your 21st century replacement for the traditional 130-year-old EKG, offering a modern, more efficient approach. It also aims to replace many of the legacy stress imaging tests that most of your cardiologists have relied on for decades. By embracing this new technology, we're not just upgrading tools, we're transforming how we approach cardiac care, making it more accessible, accurate, and safer for everyone involved. So, as we move forward, remember that innovation should always serve to enhance patient outcomes while maintaining the highest standards of safety. Thank you once again for your commitment to advancing healthcare together.